We'll continue with our binary heap like yesterday we did it. So here let's go a little bit what we did last time. So the binary heap means it's a tree-like structure and it has a two child like binary search trees. And the requirement is that the parent, there are two kinds of binary heap. One is called the max heap and one is called the min heap. In the max heap, the parent is always greater than the child. Even it's left or right, doesn't matter. Parent should be greater than child. For example, this is 16, so it will be small, maybe anything. And this child will be still small. So it doesn't matter if I comes left side or right side, but it should be smaller than parent. So that is what the binary heap means. Now, how do we insert it in the binary heap? We did this last time. I'll just go through in short. So whenever we don't have any root, we just add one node in the root with whatever value. Let's say if you want to add 100, I put it 100 here. Then as soon as I add more element, first we have to insert in the last part of the node. For example, if I add 200, so imagine we have the array. Initially it was 100. Now I added 200. So I add 200 in the last value of this array, and then I check this 200 with the parent. And since parent is smaller, so we swap the numbers. So 200 will come here and 100 will come here. That's how the binary heap or max heap works. So first we have to add at the end, and then we have to reposition it to whatever point we have to move. So for example, here if it is 10, and then we have two child 5 and 6. This is 10. Now if I add, so initially we have 10 and I add 5 and 6. Now I add, for example, 100. Since 100 is the bigger, it should go to the top, but first we have to put in the end of this array. So first we have to put 100 here. Then we have to compare 100 with the 5, its parent. Since 5 is smaller, so I will move the 100, swap the 100 with the 5. 5 will come here. And then again I will check 100 with the parent. This parent is 10, so 100 will go here and 10 will go here. So 10 will move here, 100 will move here. So the idea is first put in the end and then move based on what we have in the parent. This was the insertion. We have seen insertion last time. We have seen the coding also of the insertion, where we first push the value in the end of the array. Then we check the index of this last element and the element of the last element. Then we compare this element with the parent value, and if the element is less, then we break, because we don't want to swap if element is less. But if element is bigger, then we swap by saying the parent is equal to element and the current index with the parent value. And then we change the index to the parent index so that we can go to further parent of parent. So that way we loop it in the while and insert the new values in the binary heap, that is the max heap. Okay, now the thing is that next is remove part, which is what we will do today. So first let's understand how we remove it, and then we will write the code for it. So I will create one tree and then we will try to remove it. So let's create one max heap This is 41. Then we have 39. Then we have 38. Sorry, 33. Then we have 18. Then we have 27. Then we have 12. And then we have 55. Or let's keep it till 12. Okay, 55 will not end now. Now we have to understand Oh, hello, can you hear me? Okay, my computer suddenly got shut down, so I have to restart. So let's continue where we are. Okay, so we are doing the removal of the node in the Max Heap. So this is the Max Heap, and we want to see how to remove the element. So for example, we have 41 here. I just was trying 39, 33. Then I said 18, and then I said 27. Sorry, 27 is here, and here will be 12. So if we want to arrange that in the array, it will be like this: 41, 39, because representation of this max heap is in the array. 33, then we have 18, and then we have 27, and then we have 12. Now we have to remove the element. So generally how we remove the element, we don't give any index to remove, we don't give any position to remove. So generally removal happens always at the top level, that is this level. Removal happens at the top level. So when I say there is a max heap, and when I say I want to remove the element, that means it always means we have to remove from this top element here. This 41, we have to remove it. Okay, that's how it. Okay, so whatever the element is at the top, that will be removed from the from this array, and that is how we have to do it in the max. Okay, is that clear? What we are trying to remove? It's always at the top. So when we have to remove the element, from the max heap. The first step is remove from the top, that is this 41. So what we are trying to remove? So I will say max is, we have to remove the max element, that is the max is 41. So I will put this max value, that is the 41, in some max variable, and this will be returned. So when I return something, I will return max. But once I remove the 41, we have to do the manipulation on the other elements, which we will do it now. Okay, so that's how we will do it now. So I removed the 41, and the max is removed here at the end, but we have to do some steps in between so that all elements should be properly arranged once we remove the top element. Because the top element is the largest one, once it is removed, we have to arrange all other elements so that all elements should be in the max heap rules. So every element should be in the max heap rule. That's how we are trying to do it now. So let me write on the steps here. So first step is we assign the top element, that is max, to some variable that is called the max. So max is 41. Second step in the removal is we have to take this last element and put it at the top element. So the 41 is gone. So what will be replaced with the 41? 12 will be replaced by 41. So take out last element and put it at top. This is the second step. So what will happen now? I remove the 41 is gone. Okay, 41 is gone. It is assigned to max kind of thing. Max variable. Now 12 is also gone because we take out the 12 and we put it at the top. Okay, once we put the 12 at the top, now once I put 12 at the top, it will travel down at its appropriate position. Okay, so now third step is move top element to down, because 12 is not the bigger number. 12 is not the largest number, so the position of 12 is not good. It's not correct. So we should move the 12 to appropriate position in the tree. Okay, so what we did, we removed the first top element 41. We deleted 41 because when we remove something from the max heap, it is always the top element we have to remove. And we took this 12 and put it instead of the 41. So 12 will come here at the top position. Then 12 is not at the correct position. So we have to move the 12 down to make it at the correct position. Now we have to understand how to move this 12 to down. So let's create another one and see how to move 12 down. So we have written the steps. Let's write down a few steps now how to move 12 down. So 12 has two children, 39 and 33. So first what we have to do, we have to check whether this left child 39 is greater than the element. If left child is greater than the element, then we will put that this number in some variable, temp variable. I can say temp variable. I will put this 39 in some temp variable. Okay. Because 39 is greater than the 12, so that means this or this should go at the top level. What would happen if both are smaller? If both of these are smaller, what should I would have done? Can anyone tell me what should I have done? If 39 and 33 would have been smaller than 12, then what should I have done? Any guesses? If instead of 12 number, it would have been 55, for example, then do I have to move the 55 down? If 55 was there here instead of 12, then do I have to move the 55 down anywhere? No, because 55 is the largest number, so we cannot move it to down. Okay, so if the top number is largest, then no need to do anything. Okay, but since 12 is not the largest number, so we have to move it down. Now first I will check with the left side. If 12 is less than left side, yes. So I put this in the temporary variable. Maybe I can say left side is 39. Then I will check if 12 is less than right side. Yes, 12 is less than right side. Because 12 is the end number. So the procedure is we should take the end number, move it to the first number, and then arrange the 12 number to appropriate position. That is how we have to move in the max heap. Okay, whatever end number is there, we have to move it to the top, and then we have to arrange all the numbers again. That is how the procedure is in the max heap. Now I check 12 with the left side. Left side is greater, so I will put this left side here. I will also check right side. 12 is less than the right side, so I will put right in the this variable called as right side 33. Now, shall I replace 12 with 39 or shall I replace with 33? Shall I replace 12 with 39 or shall I replace 12 with 33? If I replace with 33, 33 will go up and 12 will go down. Then it becomes wrong structure because 33 should not be at the top. So we should always replace with the top, bigger number. So since we have 12 at the top position, we will check if 12 is less than left side, yes. We'll check 12 is less than right side, yes. But we have to check also which one is the bigger number. If left side is bigger number, then we have to replace 12 with this left side. But if right side is the bigger number, then we have to replace 12 with the right side. So the one which is the bigger, we will put in some another variable, s variable, and we will put 39 here. And then I will replace this s with the 12. Okay, so I know that 39 is the bigger number out of two numbers. So what I will do, I will take this 12 number and put it here. Because 39 is bigger, I will put 39 here. Now 12 has reached this spot. Now we have to again check whether the child are bigger or no. If child are bigger, then we have to move child to up and we have to move 12 down. So what I will do now, I will check again with the left side. So left side is 18. So we will say, yeah, 18 is bigger. 18 is a good candidate to move upward. But if I check right side also, right side is also 27. So I will check out of these two, which one is a bigger number. I will see right side is a bigger number. So this is the ideal candidate to move up. So what I will do, I will create another variable where I will put 27. And then this variable will be swapped with this 12 number. And so this one will go here, 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 and I will put here 27 and I will put here as 12. Now I will try again to see they have child or not. Since they don't have child, so that means we are end here. We are done with the tree and we are at the correct position. Let's assume instead of 12, we have 55. Now what we have to do, for example, in this case, let's say 55 is there at the last element. So I have to remove, that means I will remove 39. Top element will go away. Always removal is at the top. So 39 is removed and this will go out of the function. And we will also delete 55 and put it here at the top. Now I will check 55 is greater than these two. Yes, 55 is greater than both of them. So this cannot go down. 55 cannot go down. That means we are at the correct tree level. We don't have to do any other thing. Okay, so this is how the whole thing works. Let's write down in the coding point of view how we will try to remove it. And as soon as we'll write down, we will go through the logic again in this flow to understand whether we are correct or not. So what we have to do first, let's try to do one by one. Let's write down the steps one by one. So first step is take the top element of the tree and assign it to the variable. Okay, so we will take the top element of the tree Since this is the array, for example, I will create one tree structure. So let me create one tree structure 41, 39, 33, 18, 27, and 12. So this is the structure. So I'll say take the top element of tree, assign it to the variable. So I will create a variable called as max, and I will take the top element. So can anyone tell me what should I write to get the top element of the array? Array is nothing but this dot values. So whatever element we have put will be inside this dot values. So this dot values will be equal to 41, 39, 33, 18, 27, 12. This is the value of the this dot values. So how can I take this 41? What should I write here? This dot value, this dot values dot zero number. This is at the zero number. And this removal will only happen if we have some elements in the values. So we can check here if this dot values dot length is equal to 0, then we will return. We don't want to go further. If we don't have in the anything in the value, that means this is empty tree and we have to return null. We don't want to return anything. Now first point is we have to take the top element, that is the 41, we have to remove it. So what is the top element? Can anyone tell me? Anand has said, I want one more answer. How can I get this top element? We don't want to reduce the size of array from the top. So if I use shift, it will take 41 and reduce the size, and 39 will come at the top. We want to make this as, we don't want to remove something from here. We just want to, take this element out, which will be sent it out. We don't want to make this as key. We don't want to remove something from here. Though 41 is removed, but we don't want to reduce the size of the array. If I use shift, yeah, heap is not there. What is the heap? I don't see heap. This dot value heap. I never heard this this syntax. This dot value heap. So we have to take this 41 top element. 41. 41 is here. 12 is here. I want to take this 41 in variable. Right now I'm not deleting anything from the array. I just want 41 in some variable. That is the max variable. I want to get the 41 value in this max variable. There's no head. We don't have the linked list. Okay, so Anand has given the correct answer. I want you to repeat that answer, but everyone tried to give the different answer. So the answer is that this dot values dot 0. I want to take the top element, this one. So I'll just say this dot values 0. So what is the max? 41. So I will do some calculation here. But after all the calculation, I have to ultimately return the max, because that is what expected. Whenever I want to remove something from the max heap, it should be always the top element, 41. Okay, so we have to now recalculate the tree. What is the calculation we have to do? Recalculate the tree. Okay, so the first value is done. First part is done. We take the first element 41, put it in the variable which will be returned. Is this step clear? This part? Only this part. Still this array will be like this only. We have just taken this value 41 into the max, but we have not removed this value 41 from this array. So Olay, You cannot hear. Any other person who cannot hear me? Okay, I can hear. Okay, Ole, so you have to relog it. Maybe you go out and come back again. Okay, so this step is only we are taking the first value 41 and putting in the variable which will be returned. Still, we have not deleted anything from this array, which we will do now. We will take the last element and put it at the first element. Okay, so let's do the next step. Next step is we have to take the last element and put it at the first element. When we take the last element, we have to reduce the size of the array. Since we want to delete one element, which we have taken it out, so when I take out something from the last, I want to reduce the size of the array to 1. So that means I don't want any other thing in the last. So how will I take the last element and reduce the size at the same time? So for example, I will say constant end equal to, this is the end value equal to, what should I write so that 12 is removed from the array and size is reduced to 1. I cannot reduce the size like this dot value dot length minus 1. What is the proper way to reduce the size of the array? And also we have to take this 12 element. Okay, forget about it. How will I take this 12 element? Props, there is no props here. This is not React. If I use this dot length, value dot length minus 1, I can only retrieve the 12. It will not reduce the size of the array. Pop is the right way. We have to pop 12 from the array. So 12 will be removed and assigned to this variable end, and the length of array will be reduced. So what I will say, this dot values dot pop. So that means here 12 will be assigned to the end variable, and in the max we will get the 41 as assigned value. So max is 41, which will be returned, and end is 12, which will be taken out from the array, and the size of the array will be reduced. After this step, the values will be 12 will be removed, and this is the array after this step. Okay, so we have removed the 12, which is in this variable, and we have the array which is less in size of the previous array. Now we have to take this 12, put it at the first number, that is instead of the 41. So what should I write down here? Take the end variable and replace it with first index. As I showed you, we have to take 12, put it in 41. So what should I write here? So that 12 will be taken out and assigned to 0 number. How will I replace this 41 with 12 now? What should I write here? Correct. I will do like this. This dot values at 0 number. I want the end variable. So at the 0th position, I will replace 41 with 12. So after this step, this 41 will be replaced by this one. So after this step. And after this step, after pop, values will be like this. And initially we have the values like this. Okay. So let's try to run this and see what is the values after this. Okay, let's copy it. So I created the heap and then I'll say heap. What is the heap? Heap has the values 41, 39, 33, 18. This. So I will try to remove it now. Heap dot remove. So as soon as I do remove, you will see 12 is at the first position, 39, 33, 18 and 27 and 41 is returned. So and as soon as I run the remove, 12 will go at the top and 41 will be returned. But still it's not done. We have to rearrange these elements inside the values array. So before I go further, you can write down this part and then we can go further. Okay, so just write down this remove function. Here after end, I will put some more code here as a precaution step, but that I will do later. But at least you can write on this part. I'll give you 2 minutes to finish this. And if my computer restart again, because I think some problem has come in my computer, then I will rejoin in 3 to 4 minutes. Okay, so be there. Just copy this. Okay, so I think you might have completed this part. Now, after this part, we have this the new array which will look like this: 12, 39, 33, 18, and 27. Now we have to move the 12 to appropriate position in this. So that is the big logic which is coming here. Big logic, that is to move this end variable at appropriate position in the tree. Okay, so that is the big step. We have to understand how it does. Okay, so first let's see. We are trying to move from 12 number to down. So the index of the 12 number is 0. So we will start with the index of 0. So I'll say let index equal to 0, because we will always start with the 12 number and move downward. So 12 number has the index of 0. We will also put the length. Length is equal to, we will check what is the length of this whole array, because we should not go down the length of the array. If we have some index which is down the length of the array, that means we are done with the array. We should not go. So we should know the length of the array. This dot values dot length. We should also put this end element is there, but let's put this end element in some element. We will rename kind of this. It's not necessary, but let's say tomorrow you put this big logic in another function, and that's the reason we need to find this end value which is at the 0 position. So I'll put this element. We'll put this 12 number in some variable called as element, and this is the length 1, 2, 3, 4, 5. So the length will be 5. Initially we have to start with the index. We have to start with the 12 number. Length is 5, and the element which we want to move is 12. This element will not change because we have to only put 12 to down. Okay, so this element is the main element which we are trying to move, so that we will put in some constant element. Now we will loop it. Okay, so I will not write down the while loop first. I will just say loop number 1. What we were trying to do in the loop number 1. So after 12, I need to find its both the child, left side and the right side. So here I will write down let left child index. The index of the left child is equal to something. Let right child index equal to something. So if we have the index of the parent element, we can find the index of the child, left child and the right child with the formula which I explained you on that day. I will write down this formula again so that you can remember it. So the formula to get the left child is, let's say current number is index, or index is the current one, is the current index which we want to find the child. So the left child will be 2 into index plus 1, and the right child will be, this is the formula which I gave you last time. The right child will be 2 into index plus 2. So based on these two formula, we will find the left child index and the right child index. So I will copy here this part and put it in the left child index. Copy the right child part and put it here. So let's try to find what is the index of the left child and the right child. Current index is 0. So 0 into 2 is 0 plus 1. That is the first child. Left child is this 1 number, that is 39 number. And the right child index 2 into 0 plus 2, that is 2 number, that is 33. Is it clear how we created the left child index and right child index? So we are at the top level, that is 12 number. We need to find two child, left and right. To find the left child, we put this. To find the right child, we put this formula. And based on this formula, we get the value 39. But the child is, index is 1 here with value of 39. Here index is 2 with value of 33. We are starting with index 0. We are checking the length of the array. We are checking the element which we want to manipulate it, which we want to move in the tree. So this is the 5 step. Write down this 5 step. And is it clear, this part, 2 part, how we get the left child and right child? So index is 0. Based on the formula, we create the left child. We get the 1 number. And based on the formula, we get the right child, which is 2 number. Okay. So that is how we get the left child and the right child. Based on the formula. This is the formula. You have to remember this formula to get the left child and the right child. If we are at the 0 position, left child will be, based on the formula, will be 1. And based on the second formula, index is 0, that is 12 number. And the right child will be this 33. Is it clear? I want to know if you have understood this formula. I explained this last time also, this formula, right? Based on the formula, we get the left child and the right child. So now we get the 12 number and we get 2 child, 39 and 33. What are we trying to do now? What are we trying to do with the 12 number? Can anyone explain? We remove the 41 and we return the 41. And we move the 12 to the top. And now what we are trying to do with the 12 number? Can anyone tell me what we are trying to do with the 12 number? What we are trying to do with the 12 number? Compare is the step which we are doing. What is the ultimate goal? What is the ultimate goal of 12 number? What should we do with the 12 number? What is the ultimate goal of the 12 number? If I don't move 12 number, what is the problem? I got it. We have to swap it, Kate. You're right. But what we are trying to do with 12 number? If I don't touch the 12 number, what will be the problem? What will be the problem if I don't touch 12 number and don't move it down? We are trying to do max binary heap. In the max binary heap, the parent, Anand, you're right. Parent should be greater than all the child element. Right now, since we move 12 to the top, that is the first position, that means 12 is not the largest number of all the elements in the array. So we have to move the 12 number to appropriate position so that the parent should be greater than the child. That's the purpose. That is the purpose of these steps which we are writing. So we are starting with the 12 number and then we are moving down to its left child and the right child. So first aim is we have to find the index of the left child based on this formula and the index of the right child based on this formula. Okay, now we will go to the value. We will see the value of the left child and the right child. Because we right now only got the index 1 and 2. Now we have to take the value also. So let's put the value null and then we will figure out what is the real value. So I'll say left child value equal to null. Initially I will make null. Let right child value equal to null. Now question, can I take directly here the value by putting this dot values of the left child index and this dot values of the right child index. I put null initially, but is it okay to take like this also? Okay, so the answer is no, because we don't know whether this left child value is really there or not. Right now it's there, but sometime we are out of the bound of the array. Let's say if I want to find the child of 18, we will not get the child of 18 because array is limited. So initially we will make it null, and based on some condition, we will try to get the value of this left child and right child. Okay, so I'll come back to it in a minute. Now I will also create one variable, that is name it as swap, and initially I will make it null. And I will come back to this variable in a minute, why I have created this variable. Okay, just create this variable right now. Now we have to take this left child value and right child value. Left child value can only be taken if the index is less than the length. Is that correct or no? Left child value can only be taken if this index is less than the total length. Is it correct or no? We can take left child value only when the index is less than the total length. If index goes above the length, then can I get the left child value? No, because for example, if I say this is 0, 1, 2, 3, 4. Now, for example, if I want to take the child of 27, child of 27 is something 9 number. So I will not get the 9 number here, because 9 number is greater than the total length of this array. So I have to check when I want to take the value, that value should be less than the length of this array. Otherwise, I will not get that value. Okay, so to get the value, here I will say if this left child index is less than the length. If it is less than the length, then only we will see that left child index exists, and we will get the value. So I'll take left child value equal to, how can I get the left child value? What should I write here? How to take the left child value? We have taken the left child index as this 1. But I want to take the value, that is the 39 number also here. How can I get the value? What should I write here? Values of left child index. So I will say this dot values of left child index. So index is 1, so value will be 39 here. So the value of 39 will be assigned to here. Like we have done with the left child index, we will do with the right also. If right child index is less than length, then right child value is equal to this dot values of right child index. So this will be 33. So we got the index of 1 as one child and index of 2 as the second child. And we got the value of the first child as 39, value of the second child as 33. Now I will ask you a question. Now here I have to say if left child value is greater than the element, if this left child is greater than the element, then only I have to swap it. Okay, if I have left child greater than the element, then only I have to swap it. If this is small, then I don't want to swap it. So here what I will say, if left child value is greater than element, if it is greater than element, then we have to swap it. Swap the numbers. Similarly, okay, similarly, here also I have to say, if right child value is greater than the element, then we have to swap it. Okay, so this is little tricky. You need to try to understand. Right now element is 12. Element 12 is greater than the left. Element 12 is less than the left child. Left child is 39. So that means we have to swap it to at least 39. We have to choose which one is we have to swap. So here I will say, so whether here I have to swap or no. Question is this one. Element is 12 and the left child is 39. Is swapping needed here? Yes. Why it is needed? Because 12 is less, 39 is greater, so we need to swap. But we have to think whether we have to swap with the left child or the right child. So that's the reason we created two if condition, and then we have to think whether we have to swap this 12 number with the left child or the right child. Okay, so let's try to write down here first. Let's say I will set swap equal to left child index. At least I have to swap with the left child here after this step. Here I have to think whether I have to swap with the left side or the right side. That is what we have to do it in this if condition. Till this if condition, we only know that 12 is less than 39. So we have to swap with at least left side. Okay, so we have to swap with at least left side. Now, let's see here. Okay, let's see here. If we have already swapped it, here, that means swap has some value. I will say swap has a value of 1 because left child index is 1. So if we have something in the swap, then I have to compare whether the left side is greater or right side is greater. Okay, so let me write down like this. If swap is there, that means at least 12 number is less than the left side. That's why swap has some value in it. Is that clear, this part? Swap is initially null, and if element is less than the left child, then the swap will get the left child index. Once the swap will get left child index, that means I will say at least 12 can swap with the left side. Is that true or no? It is true. 12 can be swapped with the left side. So here, if the swap is there, that means we have this value which is greater than this 12 number. So we have to write some different condition here, which I will write down here. But there is another condition. There is another condition if there is no swap. What it means? I will say if there is no swap. What is the meaning of this no swap? What is the meaning of this no swap? Swap is false. If swap is false, that means what? That means we have not reached this part. That means left side is the smaller, correct? That means left side is the smaller. So we are not inside this part, this if condition, and so SOP is null. So that means left side is smaller than the 12. So here no SOP means left side is smaller than the element. But if SOP is there, that means we have reached this part. This means left side is greater than the element. So if the left side is smaller than the element, then we have to compare this element with only the right side. Left side is gone. We don't consider the left side. So if no SOP is there, that means left side is gone. We have to only take care of the right side. Only take care of right side. Okay, because left side is smaller, we don't care about the smaller element. We only care of this right side. So here we have to check, and we have to check if right side value is greater than the element. So since it is no SOP means left side is out of the question. We don't care about the left side. We only care about the right side. So if there is no SOP, so I will check the right side value with the element. If right side is greater than the element, then we will SOP with the right side. Right? So if no SOP is there, left side is gone. We don't care of the left side. We only take care of the right side. And if right side value is greater than the element, then we will SOP with the right side. Since we will SOP with the right side, I will say SOP equal to right side index. But what happens if SOP has happened? That means left side is also greater than the 12, like here in this example. If left side is also greater than the 12, and we have to now check whether the right side is bigger or the left side is bigger, because we have to check whether 39 is bigger or 33 is bigger, 39 is bigger. Whoever is bigger, that will be assigned to the SOP variable. Okay, so here if SOP has happened, that means we know that left side is bigger than that element. Okay, so here we have to only check if right side is bigger or left side is bigger. So here I will check right child value is greater than the left child value. So here I will check if right child value, that is 33, is greater than 39, then I will take the right side, and if it is not greater, then we already have the left side in the SOP. Okay, so here I will say SOP equal to right side child index. This is little complex. Let me go through it, and after the lecture you have to go through it again and again to understand. So let's take the 12 number. We will check with the 39 number, and since 12 number is less than the left child, that is 39, we will make the SOP as 1, index of 1, that is the value of 39. Okay, so what is the SOP is now after in this case? In this case, SOP is 1 and value of 39. We will only save the index, but it has the value of 39. And then we go to the right side. We will check if SOP has happened, whether SOP has happened or not in this case. In this case, whether SOP has happened or no. In this case, SOP is happened because 12 is less than 39. So we reach to if condition and we make the SOP equal to one number. So SOP has happened. Since SOP has happened, we have to check whether right side is bigger or left side is bigger. If right side is bigger, this is the right side. If right side is bigger, we change the swap with the right side. But if the right side is smaller, we will make the swap as the left child, which is already here. So this will only happen when the right side is bigger than the left side. So we are not inside this if condition in this case. We are not inside this if condition in this case. Okay. So let's try to go through this again. This is a little tricky. I will go to the left child of the 12, which is index of 1. I will go to the right side of the index 0, which is index 2 number. I assign to it some variable. Now I will check if left child is greater than the element, whether the left side, that is 39, greater than the 12. Yes, 39 is greater than the 12. I put this temporary variable swap with the index with which we have to swap it. That is the left side, 39. Then I go to the right side. Right side I see if swap has happened, that means left side was bigger than the element. So we have to just check if right side is bigger or left side is bigger. If left side is bigger, we already assign left side to the swap. But if right side is bigger, then we assign the right side to the swap. And if the swap has not happened, that means if we have not reached here, that means the left side is smaller. Then we have to only check the right side is bigger than the element. If right side is the bigger than the element, then we assign the swap with the right side. And if right side is not bigger than the element, then we will come out of the loop. We will break it because left side is also smaller, right side is also smaller. That's why we have put these three conditions. We'll go through this condition again in a minute because when we go to loop number 2, we will see some more things. Right now we are in the loop number 1. Now after these two if condition, I will check if swap has happened or not. If no swap has happened, that means both the numbers are smaller than the 12 number and we don't want to do anything. So we have to only go further if swap has made, if we have created some value in the swap. If swap is not there, that means both the left and right are smaller. We don't want to go further. So if there is no swap, I will use the break and come out of the loop. I have not created the loop yet, but I will create the loop while loop here. So once there is no swap, we will come out of the loop and we will not go further. But if swap has happened with right child or left child, then we have to do the swapping here. Here comes the swapping logic. So if left child is bigger, so we have to replace the element with the left child. If right child is bigger, then we have to replace the element with the right child. So which one it is bigger? It is always in the swap variable. So ultimately we have to replace with the swap index, whatever index is inside the swap. So let's write down the swap logic here. So what I will do, this dot values, whatever we have at index, that is we have the 12 at the index. We will assign the 12 with this value. This is in the swap, right child, left child index. This left child index 39 is in the swap variable. So I will say this dot values of swap. So what I am doing, I am replacing 12 with 39. And I have to replace 39 with 12. So next line will be, this will replace 12 with 39. So that means the values will become like this. 39 is here also, 39 is here also. So values will be replaced. 12 is replaced by 39. Next I have to replace 39 with 12, which was here. So here I will say this dot values swap is equal to, what is the 12? 12 is saved in the element. So I just need to replace it with element. Okay. Now, once we have swapped, so after this one, values will become this. Once we have swapped it, we have to move the index. Index was initially 0 level. we have to move the index to this 12 number where we have moved the swapped, where we have swapped this 12 number. So we have to change the index IDX. Initially it was 0. Now we have to change it to this one. This one is one number. That is the swap number. So I will say IDX equal to swap. So this completes one loop, and we will start with now 12 number, and we will go further down whether 12 is at the correct position or we have to move still down in this spot. So this is the, after loop 1, this is the final version of the values. Now we have to work, and index is 1 here. Okay, 1 means this one, and element is 12. Element will never change. I will go through the loop again now. If you have not understood, let's try to understand again. So first what I will do, now we are in this position. I will start with the left child and the right child. So we are at the position number this one. So what will be the left child of this one? Can anyone tell me the number? What will be the index number? Index is now 1. What will be the left child? So we are going to the loop 2. This is loop 2. Second time we are looping. So your left child index is 1. That is 12 number. Now what is the left child of the 12? Based on this formula. With the, when I say left child, I want the index of the left child. Index of this 12 number. Child of this 12 number. So if I put 1 inside this, 1 into 2, 2 plus 1, 3. 3 is this number, 18. So the index is 3 and the value is 18. What will be the right child of this one? Right child of this one, based on this formula. Index is 1. Okay, I want the index. I don't want the value right now. Value, I know it's 27. What is the index of the right child? What is the index of the right child? 4. 1 into 2 is 2. 2 plus 2 is 4. So index is 4. And the value of the 4 is 0, 1, 2, 3, 4. 4 is 27. So this is 27. Okay, so we got the left child as 3 and the right child index as 4. Now let's go to another step. We will keep these two null initially. Then we'll go to next step. We will create this swap as null. Then we'll go to next step. We'll check if left child index is less than length. If left side index is less than length. So this is true or false based on what we get here. This is true or false? True, because index is 3 and the length is 5. So 3 is less than 5, so we will go inside this if loop. But let's try on the right side also. Whether this is true or false. Right side index is less than length. True or false? True. So we have to go inside if condition also, in this if condition also. So now let's assign the left child value to the, if we have this true. So left child value will be this dot values of left child index. Left child index is 3, so value will be 18. Same thing will go with the right side. Right side, since it is true, we will say right child value equal to this dot values of the right side child index. Right child index is 4 numbers, so value is 27. And we are comparing 12 with 18 and 27 now, both. So let's first compare 12 with 18. So here is the logic to compare 12 with 18. So here I will say left child value, which is 18, is greater than the element. Element is 12. Is it true or false? Is it true or false? Is left child value, that is the 18, is greater than the element. Element is 12. True or false? True or false? True. Right? Since it is true, then we have to assign the swap with the left child index. So after this one, swap will be left child index. Left child index is nothing but the 3 number and the value of 18. So we get the swap with the value of 3 number. Okay, swap has the value of 3 number. Let's go to the right side now. Right side child value is 27. Okay. So now we have to say if swap is there. If swap is there, true or false? Whether swap is there or no. Swap is there. Okay, that is true because we got the swap equal to 3. So swap is there. If swap is there, then we have to check which one is greater, left side is greater or right side is greater. So which one is greater, right child is greater or left side is greater? Right side is greater. Since right side is greater, so I will change swap to right child index. Okay, so this will become true in this case. So I will change the swap to the right child index. So now what is the value of the swap? Swap is 4 number with the value of 27. And if swap was not there, which is not the case here, this is not the case here, but I will write down, if not swap, then I will check this condition, which I'm not checking it now. So if no swap is there, then I'll check the right child is greater than the element. Yes, right side is greater than the element. We would have taken the swap equal to right side child. But this is not the case here because we already got the swap equal to 2. So now the swap has a value of 4 number, right child index. That means we have to replace this 12 number with the 27. So we have to replace 12 to 27. Okay. So if there was no swap, that means both the elements would have been smaller than the parent element, and I would have break it. I would have not replaced it. But now swap is there, so that means we have to replace it. So write down the replace logic. So I'll take the index. Index is the 1 number, and I will assign the swap. Swap is the 4 number 27. So the 1 number will get now value of 27 after this one. So after this one, what is the last array? This is the last array. So here 12 will be replaced with the 27. This is how. So 12 will be replaced by 27 because index was 1 number and the swap is 4 number. We take the 4 number, put it at the 1 number. And next is this one. And I have to take the swap, that is 27 number. I have to replace the 27 with the 12 number. Element is 12. So I'll say replace it with 12. And I will change the index. I will change the index to swap. That is, index will now become 4 number because this swap is 4 number. Now once index has become 4 number, we will go down to child of this 4 number, which is not there here. So we will come out of the loop in this case. So since, okay, wait. So right now index has become 4 number, and then we'll go to the loop again, and once we go to the loop again, we don't have more child, so we will come out of the loop and we are done with it. So right now in this case, we went to the 2 loops. One loop was this one and one loop was this one. Okay, after the second loop, index is 4 number, but it does not have any more child, so it will not go inside this if condition also. It will not go in this condition also, and there will be SOP will not be there, and it will break. And once it will break, it will come out of the function, and we will return the max. So let's write down this in the loop in the proper word. So we will do here, when I start the loop 1. So here I will say while we will go on going in to the child unless we get the break. So I will start with the while true, and once the loop 1 is done, I will complete the while loop. I will delete the loop 2. Don't need the loop 2. And here I will return the break if we don't have swap. Okay, once we break it, we will return the max, that is the topmost element, and the swapping logic will happen here. Okay, so let's try to see how it looks in the real world. And there is some problem in this application, which I will fix it now in a minute. Okay, after we are done, I will see what is the values here. So let's run this in the browser, and then we are done. Okay, now I will remove it. So once I remove it, you will see what is the values. So 41 is removed and 39 came at the top one, 12 was moved to the proper position. If I try to remove it again, 39 will be removed, 12 will be moved to the first position, and then again it will be drilled down. And the following value will be like this: 33, 27, 12. Now 12 has come here. Again I will remove, 33 will be removed, and other 3 items will be rearranged in this way. So now, once I remove, now 27 is removed and others are rearranged. You will see 18 is at the top, 12 is at the bottom. Let's remove it again. So once I remove it again, 18 will be removed, but 12 is still here. Now I will remove it again. You will see I am not able to remove 12. So there is one issue in the code, that last atom is not able to remove. So we will fix that one now here. Why last atom I cannot remove it? The reason is this. You will see this. I create this max value, and then I take the last value and put it in the first 0 position. So 12 is always, we remove 12 and put it in the first position. We remove 12, we put it in the first position. So that's the reason 12 is not being removed properly. So here I will write down some condition that if the last item is there, we should not go further. So I will say, so here I am removing the last element from the values. After this, the length of the values becomes 0. And once the length of the value becomes 0, I should not go further. So here I will put one condition: if this dot values dot length is equal to 0, then return max. We don't want to go, because when I pop it, 12 element is removed. If I don't write this statement, it is this end is again getting added to the values array, and so we are going loop one by one. So here I will check if values is 0, then I don't want to go to max. So now if I do it again, so let's do again. So now we are getting null, because 12 is also removed. We don't want to have anything more. Okay, so let me revise one last time the whole procedure again, and you can watch video again whenever you get time. So we are trying to remove the element from the max heap. So how the logic works in the remove? we always take the top one, whatever is at the top level, that is at the 0th level, we put it in the variable and we return that in the end of this function. Then we take the element from the end, remove that element from the end of the array and put it at the first position. After we put it at the first position, we have to take that element and we have to go to child of that element till we get at the proper position. So we have to move this top element at the proper position by going to the child and child. So initially the index is 0 because this 12 number is at the 0 level, and we assign this to the element and we go to the loop. In the loop, what we do, we take the child of the first 0 index, we take the left child and the right child. We also take the left child value and the right child value in this step. And then we will see if the left side is bigger than the element, we assign the temporary variable swap with the left side index. Then we check with the right side, and we have to check whether if there is no swapping happen, then we check only the right side is greater than element or not. If it is not, then we break out of the system. And if right child is greater, then we assign this temporary variable with the right child. But if swap has happened, that means left side is bigger than the element, then we have to compare the right side with the left side. And if the right side is bigger, we assign the swap with the right side. And if right side is not bigger, we already assign the left side to the swap element. And if there is no swap happen, that means left and right both are smaller than the current element. We don't want to go other, we will break it out of the system. And if the swap is there, that means left or right side, either one of them is bigger than the element, then we replace the current index with the swap one, and we replace the swap one with the element which we are trying to move downwards. And we change the index to the swap element which we have, and we come out with the max. I know it's a very complicated logic. After this class, go through the video and do this problem multiple times. Try to do the same thing in this auto draw. Open the auto draw. Try to do yourself the logic to understand it better way. This is very important binary heap logic, and you have to write it down 10 times to understand it thoroughly. And it's very important. You should not avoid this logic. So that's all for this binary heap. So only two things we do in the max binary heap. One is the insert and one is the remove part. Remove is also a special type of remove. We have to remove the top element, and then we have to move from bottom to the top, and then we have to rearrange the element. That is the three things which we have to do it in this. It's a little complex. Go through the video again and again. That's all for today. Any questions?